Today we will be starting a new session on the course line commutated and PWM rectifiers. So now we have obtained the basic space vector equation in the DQ reference frame, where we have seen that we have it is very similar to the equation in alpha beta, but we have this extra term. Okay, so let us now pause for a minute and try to understand what it actually means. So let us expand it. So we have got this equation, as you have rewritten this equation, and now we split into real and imaginary parts. Okay, so v con dq is v con d plus j times v con q, and we can write the real and imaginary part of this space vector, and this one, and here it is like this. Okay, and then we take the real and imaginary parts separately. And so what we see here is something that v con d is RIGD, so which means on the, if you have a converter and it is the d axis component of the converter voltage will cause R times a d axis grid current, the grid current in the d axis, that one, and then you have an LDDT of IGD, and also there is a V grid D. Okay, this is understood. However, you can see here that there is one minus omega L IGQ, which means that the D axis voltage, the D axis converter voltage interacts with the D axis grid voltage through the filter having this RIGD and LDDT IGD IGD terms, but there is an effect of IGQ. Okay, so which means the Q axis grid current. Okay, now you can understand my terminologies are changing. Okay, I am saying Q axis current. Okay, the current is actually a single current, the grid current. Okay, it's a three-phase quantity. However, I am talking as if there are two circuits in front of me. There is a one D axis circuit and one Q axis circuit, and I am thinking like the Q axis, the current which is flowing in the Q axis, as you can understand, let me, yeah, so you can visualize it from here. You have this V con D and V grid D. Okay, so again we have two circuits. Physically there is only one circuit, but when we talk in the terms of DQ, we are thinking that there are two circuits working together. Okay, and the D axis circuit and the Q axis circuit you can see here. Okay, but this D axis current, the Q axis current, he is having a voltage that comes into the D axis, and similarly the D axis current is creating a voltage here. Okay, and this effect is called the cross coupling effect. Okay, the cross coupling effect is because of the Q axis current creating a voltage on the D axis and the D axis current creating a voltage in the Q axis circuit. This cross coupling effect actually slows down the system response if we don't take care of it. Okay, and so we will have to do something in our controller design to nullify the effect of this cross coupling term. Remember that this is our plant. Okay, this you have to understand very clearly. This is the voltage source converter when it is connected to the grid. So the plant itself has the cross coupling term. So we have to take additional precautionary measure in the controller to nullify this cross coupling effect inside the plant. Okay, this you have to understand. So here you can see, then coming back to this equation, you see this omega L IGQ is here and omega L IGD is here. So these are the two cross coupling terms which are present in the equation of the D axis and the Q axis circuits of the plant. Okay, so this is again written once more, and it is basically the same thing which we just discussed, is a cross coupling term and indicates the impact of the Q axis current on D axis voltage, and like that. Okay, so the one of the important points here is that, so we will talk about this minimization of the cross coupling effect, okay, sometime later. But one of the things that we observe is that now all quantities are DC, okay, because if you remember, when we did the Parkes transformation, all quantities became DC because we have okay, why it is DC? Because when we did the Parkes transformation, then here is the space vector. So you can see here the I grid space vector, V grid space vector, V con. Okay, this is the D axis and this is the Q axis, and D and Q axis are rotating. Okay, they are rotating, they can rotate at any speed. Okay, however, we actually align the we actually make the D axis rotate at the same speed as the grid voltage space vector. Okay, and we align the two equally. So you can see here, so the alignment I'll talk about it a little bit later, but here you see, if D axis starts to rotate at the same speed as all the space vectors, so if I am rotating, so I am standing here, okay, and I am rotating along with all the space vectors at the same speed, what will I observe? I'll observe all the quantities, the converter space voltage space vector, the grid voltage space vector, the grid current space vector, all will be rotating at the same speed as the speed at which I am rotating, standing on the D axis. So therefore these quantities all will become DC. Okay, it will become stationary, right? So that is why I have said in this statement all quantities are DC. Okay, so this is important to note, because there is something which is coming out from here, is that if you look into this circuit, okay, uh, carefully, we are having a DC circuit here, right? Suppose by some way we can nullify the effect of these two. Okay, how we will do it, we will see it later. But suppose by some way, by some trickery, we nullify this effect, then what do we have in our hand? The circuit, it is a very simple RL circuit. You can see here, this is an RL circuit with DC quantities here and DC quantities here, and this is the first step in some form of an understanding that, well, I have now a plant which is a first order system. Okay, we are getting to that point. Okay, when we are going into this DQ circuit, then we are able to visualize, okay, now in the DQ domain, this is the space, there are two circuits, so basically there are IGD and the one D axis and one Q axis, but it seems that this is basically a first order system with DC quantities which we have. So if I give a step input, I know what is going to happen, right? So the effect is going to be a first order response, right? So this is where we actually are heading towards. Okay, we will see that exactly this is what is going to happen. And by using a controller, as you know, the first order system is sluggish in response, and we will use a controller, a compensator, PI compensator, something like that, by which we'll make it a second order system, and then the whole of voltage source converter connected to the grid will become a second order system, and where we can control how much is the overshoot, how much is the settling time. We know how the second order control system works, second order system. Okay, so this is, so here from this point we try to kind of like we come to the point where we say that, okay, well, we have something which is very similar and known to me. Okay, a first order system. Okay. Now although this is intuitively being understood, but we have to first develop the small signal model of the circuit for designing the controller parameters. Okay, and we will do this one. Okay, now before we develop the small signal model, we will make a slight modification. Okay, and what is the modification that we will do? This modification is called the vector control of the grid connected VSC. Here what we do here is that the rotating D axis in the DQ reference frame is aligned to the grid voltage space vector. Okay, so which is called the grid voltage oriented vector control strategy. The term vector control comes from motor control. Okay, where we actually align the D axis or one of the axis to the generally the rotor flux. Okay, conventionally we align it with the rotor flux. Okay, in the motor control. Similarly, here also we actually align it with the grid voltage. Okay, so what is the benefit? You will see that benefit very soon is that we will lose one variable. We do not have to deal with two variables. We can deal with one variable, and more importantly is that we can have a decoupled control of the active and reactive power of the VSC. We will see very soon about this one. So that is what I was saying, that we have the D axis here. Okay, so here is the D axis which is rotating at the same speed as the space vectors, and now what we do is we align these D axis. As you can see here, this D axis is now aligned with the grid voltage space vector. We have coincided these two axes. Okay, so once we coincide, the D axis coincides with the grid voltage space vector. Okay, what happens to the equations? Okay, so when the grid voltage space vector coincides, then V grid Q becomes 0. Okay, right, and that is obvious here. You can see the grid voltage, okay, does not have any projection on the Q axis because it is fully aligned with the D axis. So Q axis, V grid Q, this becomes equal to 0, and V grid D is full of the magnitude. Okay, V grid. So if you put this into the equation back, okay, what we will see is V con D is something like this: RIGD plus LD minus omega IGQ plus V grid T. Okay, and V grid Q, which was present here, this has become equal to 0. Okay, V grid T is there, but the V grid Q has, okay, V grid Q has become equal to 0, right? So yeah, we'll come to this and we'll see what is going to happen. Okay, now is the important part. You can now put the same thing for the P. Okay, let us now put this one into the PT. Okay, and when you put it into PT, because you have V grid Q equal to 0. Okay, so V grid Q, this part is equal to 0. So what happens here is that the active power is 3 by 2 V grid D into IGD. Okay, and so P grid is nothing but this expression. Okay, 3 by 2 V grid D into IGD, right? Similarly, what happens to the Q expression? Q expression, you can see minus 3 by 2 V grid D into IGQ, right? And so this will become something like this. Now these two expressions, carefully note these two expressions. Okay, this is very important. You can see that if the grid voltage, okay, is constant, which is most of the cases, except when there is a grid voltage sag or swell, most of the time the grid voltage is constant. So if that is constant, so this part is constant. So this part is constant. So what does it mean? It means that we can control the P grid by controlling IGD. Okay, fine. So, and we can control Q grid by controlling IGQ. So we see here that IGD is responsible for active power exchange with the grid, and IGQ is responsible for reactive power flow with the grid. Okay, and if I suppose vary IGD, okay, if I vary IGD, I will be able to vary P grid. Similarly, if I vary IGQ, I can vary Q grid, and they are decoupled from each other, which means IGD, provided V grid D is constant, IGD is alone responsible for control of P grid, and IGQ is alone responsible for controlling the Q grid. So they have been now decoupled control. Okay, this is a very important conclusion from the grid voltage vector control of the voltage source converter when you align the D axis with the grid voltage space vector. Okay, so this is a very important conclusion. So based on this conclusion, we can see what is the overall controller and converter structure. Okay, here now we are seeing how we are so here is again the plant. If you remember, this was our plant. It is still remaining the same. We have sensed these quantities IG and V grid. Okay, so we have sensed these ones, and then we have got IGD and IGQ. These are sensed values. Okay, we have got the sensed values here. We have of course used the theta, and this theta is obtained from here. Okay, this sensed value is, so this IGD, this one and this one, so the IGQ goes here and this IGD goes here. Okay, these are the sensed values, right? So this is how and then there is also some references. I will talk about it one by one now. Okay, so there, what we overall understand, the overall controller structure has certain components, like we have a reference. So these are the reference, so which means that we are asking the voltage source converter that you exchange a certain amount of PG star and QG star with the grid. So this is what we are asking to the voltage source converter to do. Okay, you exchange a little bit of PG star and QG star. So this part is the reference here, and of course we have certain blocks and here, but there is also a sensed value. Okay, there is a regulator, there are some terms here, and then it goes to ultimately some switching, right? Some switching which goes to the VSC for as the effect of this controller. So let us understand what are these blocks. Okay, the first block is this PG star and the QG star. As I told you, these are the reference which we want the voltage source converter to exchange. Okay, but this again, from the previous equation which we just derived, we can say that PG star can be directly converted into IGD star. You can see here IGD star and IGQ star we have immediately converted by using this multiplying factor. Where from this multiplying factor came? Okay, you see here this equation, and here is this multiplying factor. This is the multiplying factor here. Okay, this is being used, this is the multiplying factor, and this is the multiplying factor here. Okay, so these two multiplying factors we will use in the diagram. You can see here. Okay, these are the multiplying factors which we have used here. Okay, and so this will become the reference, and of course we have the feedback, and as I told you, this is, for example, this is the feedback which is coming from here, and this is the feedback. So what am I saying? So what does this first part indicates? That two currents need to be controlled for P and Q exchange with the grid. So PG star, okay, PG star is getting converted into IGD star, and QG star is getting converted into IGQ star. Okay, so this indicates that the voltage source converter, although has a voltage source, but we are controlling in such a way that it is behaving as a current source to the grid. Okay, so we are doing a current control of the voltage source converter. It is very important to understand, because we have set this, you can see here, this is the IGD star. So it is a current control of the voltage source converter. We are controlling the current which is flowing here, this current. These currents are being controlled. Of course, it is in IABC, but basically in IGD star and IGQ star. So we are controlling how much current we are going to inject, which will eventually control what is the power being exchanged. Okay, fine. So again, the next step is this PI regulator. Okay, as you can understand, there are two regulators, one for the control of the P and one for control of the Q. We usually use PI controllers. It gives us sufficiently good performance. One advantage of PI controller is that the steady state error is 0, and we will need only 2 controllers. Okay, and so this is the very standard PI controller which we can use. It will make, so as I told you, if we have understood that the system is more or less like behaving as a first order system, so a PI controller will make it work like a second order system, where we can actually control all the parameters. Now comes the important part. Okay, and this is the 2 feed forward terms, okay, are added in the control loop. You see here there are 2 feed forward terms which I have added into the controller block diagram. Okay, now remember, why did we add this one? Remember, in the plant, so here is the plant. Okay, this is the plant. This plant had a cross coupling term. If you remember, we just derived this one. Inside the plant there is a cross coupling term, and in order to nullify, okay, so it is inside the plant, we can't do anything about it. What we can do is that in the controller, okay, we are adding 2 feed forward terms. As you can see here, these 2 feed forward terms we are adding, so that we try to minimize as much as possible the effect of this cross coupling term inside the plant, because the cross coupling term actually slows down the response of the plant. So if I add these 2 terms which is shown in this slide, then the effect of the cross coupling term in the VSC model, that can be highly minimized. Okay, and we get a very nice response. In fact, I will show you some simulation results where you will see that the VSC actually can work very fast. Okay, once you have properly taken care of all these issues, right? And after this, what happens is this VD star and VQ star. Okay, these are the reference. Okay, VD star and VQ star is the D and Q axis reference voltages for the VSC. Okay, which, as I told you, which must be converted into VS star, VB star, VC star, because we are going to work with either sine PWM or space vector PWM, which requires 3 modulating waveforms AC. So this, but now we are in the DQ domain. From the DQ domain, we again use the inverse Parkes transformation. So DQ to ABC and then alpha beta to ABC, right? And so we get this VA star, VB star and VC star, which will be used, say, in the space vector PWM. Okay, so this is overall the controller structure. Okay, where we see what are the blocks needed. Important blocks are this PI regulator and also the feed forward term here. Now before we proceed further, we have to see what is the small signal model of the voltage source converter. So with this one, we conclude our session, and I would like to see you once again in another session on the course Line Commutated and PWM Rectifiers.